Hello, my name is Bram Nauta. I'm a professor at the University of Twente in Enschede, the Netherlands, and I would like to teach you the very basics of analog signal processing. All signal processing is done in the digital domain today. But first we have to go from analog to digital because the world is analog. And what do we do when we digitize an analog signal? Let's plot an analog signal over time. So we have here a voltage versus time, and we have some changing voltages. Well, in an A to D converter, what we do is at fixed times, sample moments, we observe the input signal. So we basically take samples of the input signal, and if the number of bits would be infinite, then all these samples would be infinitely precise. But in a real A to D converter, we have levels, and we have n bits, then we have 2 to the power of n levels. And that means that the voltages that we store are just discrete values. They're not anything. So every time we take a sample, we take the nearest point that we have available, like this. And this way, we get those red dots is just a coarse approximation of my original signal. Well, the sample time, Ts, is equal to 1 over the sample frequency. And the step size over here, that is 1 LSB, least significant bit. So in order to make a very good analog to digital converter, we like to have a very high sample rate, but also we like a lot of bits. So for the same window, say 1 volt, you want a lot of available levels of your signal. Well, in order to characterize analog to digital converters, we have invented a so-called figure of merit. That's a number that tells how good your A to D converter is. Because some A to D converters are high speed, some are high resolution, some a bit of both, so it's hard to compare them. So what we say is the figure of merit, that's the number of how good that A to D converter is its power dissipation divided by 2 times the analog bandwidth, where in a simple world this is equal to Fs. Because of Nyquist, you need a sample rate 2 times the bandwidth, and then times the number of levels, so 2 to the power n. And this figure of merit is a nice number to compare analog to digital converters. And that means that if you want to increase the bandwidth at the fixed power, you will lose bits. So there's this trade-off. And we can plot this in a nice plot. So we can take a plot like this, where here we put the bandwidth on a logarithmic scale. So every grid here is a factor 10, and we have number of bits linear here. Then we can make equal power lines. So we can make lines like this where the power is equal. So for the same power, I can choose a high bandwidth, low resolution ADC, or I can take a higher resolution, less bandwidth. And this power basically is increasing. And of course, this area is very difficult to make. So in practical system, we like to be right here in the milliwatt range, and we don't want to be at the 100 watt level. Now let's take the example of a wireless receiver. We just take our antenna, and we have our signal over here, and we just make it a bit stronger with an amplifier, and then we go to our analog to digital converter with digital output bits, and then we can process it in the digital domain. Well, if I look at the frequency spectrum of such an antenna, I just take here my frequency, and here we are maybe at 1 gigahertz. It's typically a wireless frequency. And then there is maybe my little channel. It's a few megahertz wide. It's not so strong. That's the signal I'm interested in. And again, I can put that into my A to D converter, which has n bits, so I have 2 to the power of n levels. And I have a nice digital representation of my signal. Of course, if the input signal is 1 gigahertz, the sample frequency should be bigger than 2 gigahertz, else I don't satisfy the Nyquist criterion. So then you can say, well, maybe 6 bits is enough, 2 gigasample, well, that still sounds feasible. But the problem is in wireless receivers is that I don't only have my wanted signal, there are also a lot of interferers. There are many more antennas nearby, and some antennas they have to transmit to a faraway base station. So they send a lot of power, but the same power goes to my antenna. So someone else is transmitting to a faraway base station, which also comes at my antenna. So beside the wanted signal, I have a lot of unwanted signals, and I make them red here. And they can be much bigger than my wanted signal. They can be anywhere. There's no filter here yet. So if I want to make the system work, my input window is not just my wanted signal. So I have to reduce the gain of the amplifier to make sure that the biggest signal still fits into the range of my A to D converter. And no matter what I do, I will need to extend my range of the ADC, that all these interferers also fit into the window. So then I need a lot of extra levels, and thus the number of bits just goes up. Where I maybe need like 6 bit here, maybe I need 16 over here, because those interferers can be huge. And then I have a problem, because then I need to have something like 16 bits and 2 gigahertz bandwidth or 2 gigasample sample rate. And then if I take that figure of merit that I just introduced, I end up with a power in the order of 100 watts. Well, that's a bit painful in your pants if that's in your phone. So that's not a good idea. So this is why we need to do something analog before we go to the analog to digital converter. So here we have our antenna. We have to do some smart things here, and then we go to the ADC and we have all those bits out, but we want to remove those unwanted interferers basically, because it's a bit overkill to bring them in the digital domain and remove them over there. So we need to do analog signal processing here. And analog signal processing basically consists of 3 basic functions. One is amplification. So we make smaller signals, we make them bigger. You can do that with amplifiers. Another one is filtering. For example, a low pass filter where you have a lot of high frequency noise on your signal. You can remove that noise. And another component is the mixer. It's a frequency translation where I can pick up a frequency band and drop it at another frequency band. And with these 3 ingredients, I can make a circuit that convert my antenna signal to the digital domain. So amplifiers are quite easy. Everybody knows amplifiers, I guess. Filters, well, we can have band pass filters, low pass filters, high pass filters, and band stop filters. Well, in radio receivers, most of the time we like band pass filters or low pass filters. And then mixes is a bit of a strange circuit. But let's have a little look of this. So we have here a sinus of omega 1, and we have here a sinus omega 2. And then if you multiply those two, you get some outputs, but there's also the output of sinus omega 1 minus omega 2. So you get the difference in frequency out. And what is interesting, if I have amplitude modulation, so I have here A1 and I have here 2, then here we have A1 times A2. And if we have a little bit of phase, so phase 1 and phase 2, that phase 1 is added over here and phase 2 is added over here. So this is something interesting, because I can take a high frequency signal that I want to receive, which may have amplitude modulation or phase modulation or both. I multiply that with a clean sine wave that I make myself with a fixed amplitude and a fixed phase, and they're very clean, very stable. Then the outcome is some some signals, but one of the terms that comes out is the frequency difference. And the amplitude of the signal is proportional to the input amplitude, and the phase is also proportional to the phase of the input. So I can basically keep my amplitude modulation and phase modulation, I can keep that intact, and I can bring it to a lower frequency. I also get the sum frequency, so in fact this other term was omega 1 plus omega 2. That's a very high frequency, in case I choose these to be very close. So what I can do is I can make this one, this is my 900 megahertz, for example. I can make this 901 megahertz, and then the difference frequency is 1 megahertz. So instead of an ADC that has to digest 900 megahertz signal, that's very big, very high frequency, I only need 1 megahertz now. So that's 2 orders of magnitude less in frequency, and that means 2 orders of less power in my analog to digital converter. So that's very helpful. So now let's have a look at the block diagram of a modern receiver. If I have the antenna signal, first we amplify the signal a bit so it can enter the circuits that come after it, and that those circuits don't add too much noise. And then normally the first circuit we meet is a mixer, where we mix with a local oscillator signal. That's just a very stable, clean sine wave. And what happens then, if I take my frequency spectrum over here, and this is my wanted frequency, so this is the frequency I want to receive, this is my 900 megahertz, then I just multiply with a little bit higher frequency or lower, and then at the output of the mixer, this frequency difference, so the difference is 1 megahertz, at 1 megahertz I get that output signal. So this one is in fact down converter by the mixer at 1 megahertz. It's the same amplitude and the same phase information. I also get the sum frequencies, so at double the frequencies I also get something like that. Well, I'm not interested in that. So I take a low pass filter just to filter away the signals I don't want. So the low pass filter is basically a low frequency, that's maybe 1 megahertz filter. And at that moment I have my signal at a much lower frequency where the amplitude and the phase is still there. Well, if you do this correct, and then I have big interferers, for example, here is a big interferer I'm not interested in. That interferer has another distance than 1 megahertz to my local oscillator. It's maybe 2 megahertz or 3 megahertz. And that means if it's down converted, it will not fall right here, but it will end up, hopefully, here. And then that signal is removed by my low pass filter after the mixer. So these filters and mixers, they do something useful. The filters remove interferers and the mixers bring the signals down to a lower frequency. So if I again go to my ADC figure of merit plot, I have here the bandwidth, number of bits, and then we have all these equal power lines. If we put the analog to digital converter right at the antenna, we would be here. But by bringing down the frequencies, we basically reduce the bandwidth of our ADC, because we only have to convert 1 megahertz, or just a few megahertz, instead of gigahertz. So by taking the mixer, we go to a lower frequency. And then by using the filter, we can remove the big interferers, and we can make sure that we don't need all these levels. So that means that the number of bits can be reduced. And that means we go here. So basically, we've made this move. So this is the effect of the mixer, and this is the effect of the filter. And the amplifiers are there just to make the signal so big that the rest of the circuits don't add their own self noise. So those circuits can be low power. And by doing this analog pre-processing, we can really relax the ADC demands, and this way the analog to digital converter becomes feasible. So by adding amplifiers, mixers and filters, we can really make much more signals digital than we normally can. Okay, let's have a look at how these blocks work. Let's start with the amplifier. Its symbol is just a triangle. In high frequencies, amplifiers are very simple circuits. For example, an amplifier can be a single transistor with a load resistor, and then if you increase the voltage over here, you get more drain current and this voltage drops down. And if this transistor has a transconductance GM, that means that the drain current I is GM times V in, where GM is the small signal transconductance, then that current flows into the resistor, and then the gain is GM times R. Well, for high frequencies at the antenna, we like 50 ohm input because the antenna is 50 ohm and the cable going to the circuit is also 50 ohm. So normally people add impedance matching, which is often an inductor and a capacitor there. What that circuit does, it has passive voltage gain at a specific frequency. So if I have the resonant frequency in here, I get free amplification over here. And that's because here I have 50 ohm and I basically bring it to a higher impedance like you do in a transformer, and then I can get like 10 dB extra amplification. And that means that the circuit behind it can have a little bit more noise because we already have passive amplification. So the amplifiers right at the antenna are typically very simple circuits in the order of just a few components as I've drawn over here. Filters. Well, filters at high frequencies are built with inductors and capacitors. So this is, for example, a bandpass filter. I have here my signal, there's a source impedance, and then I have a resonant tank, an inductor and a capacitor, and they have a bandpass characteristic. So if I make a plot gain versus frequency, then at the resonance frequency I get my highest transfer function. At low frequencies the inductor is short and I get small output signals, and at high frequencies the capacitor is short and I also get no output signals. So that's a bandpass characteristic. At baseband, so after the mixer, we normally like low pass filters. So a very simple low pass filter is an RC filter that has this famous first order low pass characteristic. And of course, if I want higher order, because normally you like higher order because you want to remove the interferers and also you want to prevent aliasing in your ADC. So then you could say, let's put a big cascade of those first order filters. For example, third order is quite popular. But since a first order filter has a roll-off like this, if you cascade 3 of them, you get in the end a steeper slope, but it also takes a shortcut. It's not very sharp. So what we like for these filters is to be like this and then go steep. But if we just cascade a few first order filters, we get a really round response. And here my wanted signal is attenuated and I can correct for that, but then I need extra bits in the digital domain, and that's not good. And why is that? Well, if I look at the mathematical properties of such a filter, all the poles are on the real axis, and that gives this a round shape. If we want to make a steeper filter, we will have to put the poles more complex. So this is a third order filter where we have 2 complex conjugate poles. They are complex and 1 is real. And if we would make that as a filter, we could make a filter that behaves like this. So normally the steeper it drops, the more ripple you get over here, but you can make better filters. But just with passive resistors and capacitor, that is impossible. And that's why there are more complex filters, and they were very popular in the 1930s, 40s. What people do is, okay, let's take the source impedance, take a first capacitor, inductor, and a capacitor, for example. This is a filter where you can make complex poles. But now we have introduced an inductor. And an inductor was good at these gigahertz high frequencies, but for megahertzes, these inductors become so big that you cannot put them on a chip. You have to put them outside, and yeah, that's not very practical. We like it all integrated. And that's why we can make active filters that behave like as if they were inductors. In order to emulate inductors, we can use transconductors or voltage to current converters. Those are simple circuits which are denoted with a GM, where you apply a voltage and you get an output current. I is GM times the input voltage. And with two transconductors and one capacitor, I can make a circuit that behaves like an inductor. Let's see how that works. I take this circuit, I connect a capacitor here, and I take another GM block, but I flip it around and I give it a negative sign. So it has a -1 multiplication inside. It senses this voltage and it injects a current over here. And now we can calculate the impedance that I see over here with respect to ground. So what happens is I apply a voltage, I get a current. The current is flowing into the capacitor. It generates a voltage. That voltage is sensed by this transconductor and it takes a current proportional to that voltage. And because a capacitor and an inductor are in fact the same mathematical components, except voltages and currents are flipped, by taking two transconductors I also go from voltage to current and vice versa. So this way I can make a circuit that behaves like an inductor. I will show you the mathematics. So the inductor we see is equal to the capacitor divided by GM squared. So this circuit behaves like an inductor, but connected to ground. But in the filter I wanted to make, I have more like a floating inductor. So what I would like to make is this circuit. Well, that's also possible. I can do it like this. I can say, let's take that resistor, take a capacitor, I take my two GMs with one plus and one minus that make it look like a grounded inductor. But I can take an opposite GM, here a negative and here a positive one to that capacitor. And now what this capacitor sees, what that capacitor sees over here is a current entering here, but also a current exiting here, because this voltage pushes a current into my capacitor and this one pulls a current out of my capacitor because I have this minus sign. So then it looks like this is indeed a floating inductor. And then what you can also do, you can say, well, this voltage source with series resistor I can replace by a transconductor with a resistor to ground. That's the Norton or Thevenin equivalent. And this resistor to ground I can make with a transconductor, a minus GM with unity feedback. And this way I can make a filter with only transconductors, and it looks like this. Well, you may think, how can you make a transconductor? Well, a very simple one is a CMOS inverter with a PMOS and an NMOS transistor. If you bias that one in the middle, so not like an inverter, but somewhere in the middle, then if you increase the voltage over here, this one starts to sink a current, and this one starts to sink a current as well, so you pull a current in. So this has a negative GM. And positive and negative, well, many circuits are differential, so everywhere where there's a positive signal, you also have an anti-phase signal, and then you can just take wires from the other side, and then you have opposite signals. So if you want a positive GM, you take the signal from the other side. And you have to take care of your common mode stability. There are some issues, but basically an inverter can already be a GM block. So it can be very, very elementary. Okay, then mixers. How can we make mixers? A mixer is ideally an analog multiplier, but it's very hard to make a clean sine wave with low noise. So in practice what we do is we use a square wave. We multiply with a square wave, and that's fine because we want to make this frequency, and if we make a square wave we also get the third and the fifth harmonics, so we also down convert radio signals at 3 times or 5 times the frequency we're interested in. But if we make like a bandpass filter first, those signals are already removed. And then making a multiplier with a square wave is in fact very easy. It's just a set of switches. So again, in a case of a differential signal, if I multiply with 1, I just take the wires like this. And if I multiply with -1, I just put switches so that I just cross between plus and minus. So this way I can multiply my signal. I can multiply my signal with +1 or -1, and that also does down conversion. So in practice, a mixer is a circuit with 4 transistors, 2 to pass them on, and 2 crossed ones to send them to the other side. So that's just 4 transistors. So it's a very elementary circuit. So before entering an ADC, we can make the signal better with amplifiers, with filters, and with mixers. And these circuits can be very simple. But these circuits, they also add noise. And there's a fundamental relationship between noise coming out of the circuit and the power that the circuit dissipates. And I would like to illustrate it with a simple example. I take a 1-stage amplifier, just an NMOS with a resistor, and maybe a capacitor to set some bandwidth. There's an R and a C, and this one has a W over L. And I play with the input voltage and I get inverse gain over here. What I can do is I can take that copy of the circuit. I can say, well, copy, and I say paste. I put it here, and then I interconnect all the wires. So I just take all the nodes, I connect. What I've made now is in fact exactly the same circuit, but now with 2 times the capacitor, R over 2, and 2 times W over L. And the interesting thing is that compared to the original circuit and this one, the gain is the same, the bandwidth is RC, but here it's also RC because R smaller, C bigger, and the gain is GM-R. Well, here the GM is 2 times bigger and the R is 2 times smaller, so the gain is the same. So all the properties are the same except noise, because here we have like a lower resistor and then also we have less noise. And what this circuit does, it burns 2 times the power because I've basically put 2 in parallel. So I have my power dissipation times 2, and my noise power is in fact divided by 2. So minus 3 dB, and this is plus 3 dB. So what you can do in analogs pre-processing is, if your noise is too high, you can take copies of your circuit, put them in parallel, connect all the nodes, you increase the power and you lower the noise. And you can also do the opposite. If the noise is still fine, it can be bigger, just cut off slices of your circuit and save power this way. So this way you can optimize the power and noise of your pre-processing circuit. So I've given you a little course now how to do pre-processing before entering an analog to digital converter. It's about gain, filtering, and mixing. I've shown you how these can be implemented on a chip with transistors without inductors, for example, and how you can scale those circuits to meet the noise specification. So this is a bit of an introduction to analog signal processing before you enter the AD converter. Okay, that's it. Thank you for your attention. Thank you for your interest, and I hope you like this presentation. Thank you.